as completeness. This is a work with Valentin Benedetti. Is a student that now has started a postdoc in ICTP. Kawashigashi and Roberto Longo are mathematicians working in algebraic quantum field theory, and Javier Magán is a colleague here at Bariloche. Well, this is the plan of the talk. I will start talking about what is, for us, is completeness, because this idea, maybe people have different ideas about what is completeness. For us, we have this idea that completeness is Haag duality, and we'll show what this means. And then I will connect this idea of completeness in two-dimensional shifties with the S transformation of modular invariance. And I will show this identification through Renyi entropies that are connected with partition functions. Then one can try to see what is the amount of incompleteness of a given model, and this can be measured by an index, a particular number that has a kind of a geometrical interpretation or group theory interpretation, let's say. And then I will show some cases with infinite index, and at the end I will show some similar results that can be obtained in higher dimensions. So, but then let me start from the beginning to talk about this completeness or incompleteness. I will talk about non-local operators, and then I will draw some region. For example, this region R prime will be the outside part, and then I will take some operator here, this red one, that is kind of a Wilson loop inside the annulus. And I will say that this Wilson loop is a non-local operator in R because it's localized in R in the sense that it commutes with local operators outside, but cannot be generated by local operators in balls inside the annulus, because it's a kind of, if I have to obtain it through local operators, I have to do a flux over the whole thing that is not in the annulus. Or if I have it, I can produce it here with the A mu that is not a local operator. So this is a non-local operator, is something that is localized in the sense that commutes with outside with outside local or field operators, but cannot be generated locally inside the region. To put a more structure, I would say that the additive algebra of some region is the union or the generated algebra of all algebras of little balls inside. This is the additive algebra. The maximal algebra of a region is just the commutant. This prime in the region is the complementary region. The prime in the algebra is the commutant algebra. All the operators are commuted with the algebra. So I take the maximal algebra of this region as the algebra that commutes with all local operators outside. So when these two are not equal, what happens is that we have these non-local operators. The maximal algebra is the additive one plus some other operators. Some other operators that I will call it non-local operators. When this happens for a region, the same happens for the complementary region. If you have non-local operators for some region, the complementary region have also non-local operators. This is obligatory because of von Neumann double commutant theorem. And so these A's and B's, for example, here, a kind of Wilson loop, and for the complementary region would be kind of Toff loop. These A's and B's are dual non-local operators and cannot commute to each other, all of them.
Sorry, Horacio.
Yeah.
Which theorem is this? You said where they have to be in
No,
there?
this is I said the von Neumann theorem. Von Neumann theorem just tell you that the commutant of an algebra is equal to the algebra.
Right.
So here, if I take the commutant of this equation, I get the equation here. So it cannot be that suppose there is no local operators here, so these are not there. So these algebras are equal. The commutant of this is this one. The commutant of this is this one. It has to be that these are equal, so there is no local operator here also.
I see. Okay, thank you.
Okay. So, so for us, this is a description, this idea of Haag duality violations. Haag duality is the idea that suppose that the maximal algebra and the additive algebra are equals. This is Haag duality. So this idea of Haag duality violations, because they are not equal, there are some non-local operators, is the idea of generalized symmetries. So for us, generalized symmetries either are Haag duality violations or are something else that is not very physical. Well, but this is our point of view. Of course, people think in different ways. Okay, then what is completeness here? Well, the idea of completeness.
You've frozen, Harash.
That generated by
Cannot hear. Cannot hear.
He's left.
This is our idea of completeness, and this means that the algebra generated by local operators is the maximal one compatible with causality, means that all operators are commute with the outside part. Yes?
Horacio, we couldn't hear you from the time you started talking about this transparency. Could you start again from this transparency, please? We lost you.
Transparency, from this transparency on. Right?
Yes.
So then, connected with this idea that Haag duality violations on non-local operators, we have an idea of what this idea is just Haag duality. It means that the algebras generated by field operators, by local operators in a region, are equal to the maximal ones that are compatible with causality. In other terms, this is the algebra generated by local operators, by field operators, let's say in a region. This should be equal to the maximal one compatible with causality. It means that is the algebra commutant of all operators localized outside. So this is the maximal. So these two are equal. And this is the idea Haag duality. That is Haag duality for the additive algebra, right? For the algebra generated by local operators. So this is an idea of completeness that in fact coincides with the usual idea of completeness. I will say why. But this idea of completeness is equal then that the Haag duality for the additive algebra, or appear when Haag duality is violated, or is equal to the absence of non-local operators, and is also equal to the uniqueness of the assignation of algebras to region, because if you have Haag duality violation, you can start playing the game of choosing algebras that are not additive for your region, and it will be compatible with causality. So, for example, why this idea coincides with the usual idea of having for gauge theories. For example, Wilson loops. Sorry?
We're losing you every once in a while. We can't hear you, Raj. So sorry.
Oh, sorry. Sorry. we are in trouble then. Maybe.
Yeah. Yes. Yeah. Please continue.
Oh, sorry. Let me have an escape. Can I? Can you hear me now?
Yes.
Yes. Now it's better.
Let me see.
If it continues, maybe we can try turning the video off or something.
Is everybody having this problem with our connection? Spencer, you also can't hear. Horacio.
Yeah, this is
Yes,
it's the
yes,
same
I
problem
can't
on
hear.
Zoom also.
I can't hear.
You can't hear now?
No, now we
I
can hear.
but you're dropping once in a while. You're dropping once in a while, so
Okay,
many things are getting missed.
okay.
Maybe
Yeah.
you can try turning your video off.
My video, let me
Yeah,
try.
just save bandwidth.
Let me see. Mm. Here. I took my video off then.
Yes. But
Yeah.
Let me share screen. There.
great.
Well,
Sorry,
Well, then-
Horacio, can I
Yes.
take the opportunity to ask you a question though, just on the first line of this slide? If I may.
yes.
I'm not quite understanding the connection between this notion of completeness and causality. Because let's say we take a space like slice, then in a Lorentz invariant theory, the operators will all commute with each other. I guess your point is the Wilson line being non-local will not be part of the. What exactly is the connection between causality and this notion of completeness that you're defining? I didn't fully understand it.
For example, let me go to this paragraph here.
Okay. Yeah.
Then, if you have Wilson loops, these are non-locally generated in a ring-like region because you need the magnetic flux inside, let's say. But if you have charges, they can be broken into Wilson lines, so they are made additive in the ring region. It's important that here non-local operator, this non-local operator is a non-local operator in the region R. And it would be local operator in a ball because it will be generated by local operators in a ball. So the notion of non-local operator is a relative one to the region. So in this case, you have Haag duality violations for a ring region, right? But not for a ball. And for a ring region, if you have electric charges, you can break down the Wilson loop into pieces. And then it will be additive. It will be additive. So it will not have Haag duality violations. So in that sense, a theory with a complete lattice of electric and magnetic charges is complete in this sense. And it's exactly complete.
I see. And I guess the connection with causality roughly is that, in the additive algebra, if I'm making little balls, say on a space like slice in a Lorentz invariant theory, then the operators will definitely commute with each other. Whereas this is a non-local operator, so it need not have that kind of commuting structure. Is that the connection with causality?
Yeah, it's important that all this can be said exactly in the same way in any theory that you have algebras assigned to regions in a space. You don't really need a space-time. If you mean causality here is meant as commutation at a space-like separation. That's only that's meant here.
Right. Okay. Thank you.
But just to follow up on that, I mean, suppose you had this ring-like region in pure gauge theory, then by your definition, this theory would not be causal?
No. By my definition, this theory will have Haag duality violation. Will have some operator that will not commute that will commute with everything outside, but cannot be locally generated inside the ring.
Yes.
So
And what would you say about causality that set up?
No, it's the maximum. So what I mean by completeness is when the local algebra, the one generated by small balls inside, is the maximal one compatible with causality. So it's the maximal one that commutes with the outside part. It means that cannot have the Wilson loop here, right?
Yeah, okay, get it. Yes.
Okay.
Causality is used just in sense of commuting.
Right.
Yeah.
So, for example, another example where when you have a theory that is not complete, that is very easy to picture, is you have a theory and a global symmetry group, and you construct the theory that is the neutral operators, all the neutral operators. So in this case, you have Haag duality violations not for a ring, but for regions that are that are disconnected, like these two. For example, you have a charge here and the anti-charge. The charge-anti-charge belongs to the theory, but the charge is not an operator that can be locally produced in the ball because it's charged, and you don't have any charge operator. So you have the charge-anti-charge operator belongs to the theory, and it will belong to the commutant of the outside part of the two balls. Again, you have violation of Haag duality, and the non-local operator in the outside part is just a twist. Is a representation of the group symmetry, but acts only in some compact region. And this twist, you can say that is a non-local operator that belongs to the outside part.
So that non-local operator is the integral that measures the conserved charge.
Exactly. You can picture it as an integral on the ball of the density of charge. This thing will commute with neutral operator here. So in that sense, it commutes with the local algebra in the two balls, but it will not commute with the non-local part of the algebra.
So, but it will be generated by, it's an additive thing, right? Because if it is a integral of a current, why does it not fall
it's
under
an
your
integral of the
additive
current,
technique?
but yeah. So it's important that when you say a non-local operator, you have to say a non-local operator for some region. Here, this twist is a non-local operator for the region that is outside the two balls. So it's an integration of the charge density, but not in the outside part. You need to cross the ball, right? It's like in the case of the Wilson loop. You need to define it in terms of the magnetic flux. You need to cross the outside part, and you are thinking that the operator is non-local in the outside part. So it's not really, you cannot really write this operator in terms of local operators in the outside part of the two balls, right? In that sense, it's non-local. It just commutes with the local operators outside. This is true, but it cannot be generated in the outside part. So, and I will, well, then an important point is here is that in general, all non-local operators, these Toff loops or Wilson loops, are attached to some region, and they are non-local in some region, but they are locally generated in some other regions. For example, all these operators are locally generated in a ball. So this means that all these operators are ultimately generated by field operators, And then you can say, for example, if I have a CFT and I describe my CFT by primary fields, by the operator product coefficients and the dimension of the fields, the bootstrap data, I do not need anything else to describe generalized symmetries or Haag duality violation. I do not need anything else because it's already in that data that the non-local things appear when you analyze commutants of regions, right? So there is nothing else that you have to add to the theory in order to have these things. They appear or not already from the local algebra. So one can ask this question: what is the imprint of Haag duality violations or generalized symmetries that, in our point of view, are the same things in the bootstrap data? How can you detect that some bootstrap data contain some of these things or do not contain it? For example,
in the case of a field theory where you just restrict to neutral operators,
yes,
I suppose we believe that is not by itself a consistent field theory. in the sense that it would not be consistently defined on a torus, things like that.
Well, that's the point of my talk. That's the point of my talk. That's the point of it. So I exactly will go to that, and it's not that I contradict anything that people, but I think I want to clarify some things that people think in different way. But well, the important question here will be how to diagnose some generalized symmetry, some Haag duality violations from the CFT data. And I will reduce this problem more and more. The first reduction is I will try to see what is the diagnose of this type of things, but only for this type of neutral things, this type of Haag duality violations for two balls, let's say, not for this type of Wilson loop thing that are much more difficult. So how do you diagnose if a CFT data is the neutral part of another one under a symmetry group, right? And some people would say, well, this is not consistent. Well, I think it's consistent. The algebras are perfectly consistent. Unitarity is consistent. Everything is consistent. Something else fails. And well, what I will say is that what fails in two-dimensional CFTs, I will reduce the problem more and more. And this now I will analyze only the CFT in 2 dimensions. And for 2 dimensions, this the completeness question of a CFT data is exactly this S modular invariance. This coincides with the S modular invariance.
So completeness property is the property that every region should be Haag dual. Every region its complement should be Haag dual.
In this case, in 2 dimensions for CFT, this completeness would be the case that you have 2 intervals now, 2 intervals or many different intervals, and in the algebra in the 2 intervals generated by the local fields is equal to the commutant of the outside part. So you don't have really non-local fields. So it would be the case if you have, for example, a 2-dimensional CFT and you take the neutral part, then you don't have this. Then you have a Haag duality violation because you have one charge field in one interval and the anti-charge in the other one, and this is a non-local operator, right? So it would be complete in the sense that you have a maximal set of fields, let's say, a maximal set of fields. And
So if we take modular invariance to be a good thing, then in that particular example of this restricting to charge invariance, this lack of completeness was a bad thing. I wanted to understand if it's always going to be bad. Like every time you have lack of completeness, are we going to say that something's bad with the field theory?
Well, exactly. Well, this is important. Because modular invariance is usually invoked as an axiom, or even people say unitarity. This is not correct. But there are perfectly good models that are not modular invariant. For example, if you take just the stress tensor, for us it's completely unitary, completely normal model. It doesn't have a modular invariance. It's just a stress tensor. It closes an algebra in itself. You don't take any primary outside the stress tensor, and there is no problem with this theory, right? No problem at all. But people do not like it. Well, this is another thing. You say, well, you can not like something, but still be consistent in the sense. It's important is in the sense of a quantum local theory, relativistic theory. In this sense, is perfectly consistent.
But it's not diffeomorphism invariant on a general manifold.
Right. Or just even on the torus under large diffeomorphism.
Well, why you are talking about diffeomorphism? I'm talking about quantum field theory in 2 dimensions, right?
Okay, but then you're saying there's a preferred time direction and a preferred space, and I can't.
Exactly. Of course. I'm not saying I'm not saying absolutely nothing that is strange. Is exactly you have a preferred time and space direction, and you can see this some kind of in the torus is some kind of twisting that you have to apply to a. I will go to that briefly. Well, let me then make more precise. Then, how to make the connection of these two things? Well, it seems that in the algebraic literature, this was proposed in 2001, and there were some unpublished proof by Kawashigashi and Muger and Longo, and then we wrote to these people, to Roberto Longo, say, well, where are the because they have some theorems stating this, but they don't have the proof in this problem in these papers because they refer to other, and you follow the literature and you never find the proof. And then we wrote to these guys and say, well, where is the proof? And it was never published. And then they join us and they publish their mathematical proof of this. But for us, we follow these Renyi entropies that are very nice because it have a connection between the partition functions through the replica trick to the local algebra. So it will be somehow this connection is this modular invariance. Usually people think in terms of partition function, and this completeness idea is in terms of algebra. So the idea is very simple, that you have the Renyi entropy that is defined in this way in terms of the density matrix. This is the Renyi entry for one interval. And for two intervals, it's better to express the entropy of two intervals, just adding the entropy of the single interval to form something that is called the mutual information, because this thing automatically, this subtraction kills divergences. So this thing is well defined for the CFT, and then as it's a function of two intervals, it depends only on the cross ratio, that is a single number. So I will write this mutual information, Renyi mutual information, in this way. This is an arbitrary function of x, and this is just precise logarithmic. It is a kind of caprice here. But the reason why I'm dividing the mutual information in this way is because suppose now that if you have the two intervals and you have the two intervals in the outside part, suppose now that as usually people think that the entropies in a global pure state are equal for complementary regions, if I apply this, I doing some little calculation and having divided the mutual information this way, I can obtain that this UN function is invariant under changing x by 1 minus x. So somehow this idea is equal to the fact that the entropies for complementary regions are equal. But here is the point, because the entropies in a global state, pure state, are not equal for complementary regions, but are equal for commutant algebras. So I have an algebra, the entropy is equal for the commutant algebra. And we have seen that the commutant algebra for the additive algebra of two intervals, generated by fields, it can be something outside that is not just the fields, but it can also have non-local operators. In that case, this will be true, but these entropies for complementary region will not be equal. So it can be the case that this law fails. And this somehow reflects Haag duality for two intervals, or what is completeness. So completeness is equal to this relation. Now, this is just an example. This is a chiral scalar. The chiral scalar is just the derivative of a scalar field of mass 0, and it's a current in the sense that it coincides with the current for a fermion. It's the same theory as just the theory of the current of a fermion. In that sense, it's automatically not complete because it's the neutral part of a free fermion and the U1 symmetry. and you have these commutators, and with that you can compute the non-local operators, for example, that are just the integrals of the current from one interval to the other that crosses the outside part, but of course commute with local operators outside, because this is just the difference of the fields in the two intervals. And for non-local operators that are linked to each other, they do not commute, right? So this is a typical case of taking the neutral part of an algebra. In this case, the free fermion, I take the neutral part, I take just the current. And then you get that this U is not symmetric, and in fact, it diverges near x equal to 1.
So if we use the replica trick to compute this entropy, but that's what
Exactly. Here, replica trick. Exactly. We are there. Exactly. This is what was my following step. Use the replica trick. Here is just you have your manifold replicated, in this case 3 times, and then at the end your manifold, it has to be sewn together in a cyclic way in the cuts here, and then you have is a perfectly good manifold, except that there are conical singularities at the extremes. Well, but the important point is that this is n equal to 3 for n equal to 2, and for 2 intervals, the resulting manifold has genus 2 and can be conformally mapped to a torus of some radius 1 and some height that I call here L. This is in the paper by Hadrick, but I think many people have worked in different ways in this type of mappings. And then what you get is a relation of the mutual information, the Renyi mutual information for index 2. For index 2 is important, with just the partition function in the torus. And this is the relation. The relation between the parameter of the torus and the cross ratio of the 2 intervals is complicated, is given by these things. But important that the size of the torus going to 1 over the size of the torus is the same transformation as x going to 1 minus x. In terms of the function u, this is what you get. And you can see this part is completely symmetric in x1 minus x. So you can define an asymmetry of your u function in the case that the theory is not complete, and then this is equal to exactly to the asymmetry in the partition function and the modular transformation. They are the same. So this shows that the asymmetry in the Haag duality that you can see precisely because the entropy of complementary regions are not equal to each other is equal to the asymmetry in the partition function because there is no modular invariance. Another commentary is that in this case, when there is no modular invariance, the replica twist cannot be written as a local field on the boundary. People usually take the replica twist and say, well, I do the orbifold, so immediately these fields that are non-local, that are produce the symmetry in some region, can I write it in terms of fields, local fields on the boundary, in the extreme points? But this is not possible if your symmetry moves non-local operator, changes non-local operator. So this idea, because otherwise, if you can write in this way, you can prove this property here. So the idea then is as you know, is quite simple. In general, one thinks that you have a complete model, you have a partition function with a local Euclidean invariant Lagrangian, and then doing the path integral here or doing this is the same. If I don't put nothing in the boundary conditions, then it's the same thing. So you would expect this modular invariance, but suppose you have, yeah.
Slightly conjecture question. So the previous example we were talking about the parallel stable, you can't put that on a lattice, right?
Oh, I couldn't get it at the end.
you can't use a lattice regulator for it, right?
A lattice regulator.
Yeah, for the previous example, the chiral scale.
Ah, the chiral, you say the chiral scalar. In fact, we have done the calculation with a chiral, with a lattice, but it's a kind of chiral lattice in the direction of the null. Yeah, but you can do the calculation with a lattice in the null direction, let's say. It's in our paper, in one paper 3 or 4 years ago.
Okay.
But suppose now that you want to talk about only the neutral part of the algebra. So instead of having these two fields, you want to only have these fields, and then you can just project the states or your operators on the neutral part, and for that you have to insert this operator here. And of course, in that case, the symmetry, geometric symmetry is not there anymore. And in this case, precisely what happens is that you have Haag duality violations because you have this operator is non-local in the two intervals. It's still there because it's neutral, but it's non-local. So this is the way, this is very simple, the idea how these things are connected. And then you can try to understand what this asymmetry in general will be complicated function of the cross ratio or the size of the cylinder of the torus. But then you can compute, for example, the partition function of the theory with respect to the complete one. So here, in order to define this, I'm thinking the path integral, I made it in a complete theory, and then I insert something to produce the path integral of my theory T. In this case, this ratio is just the expectation value of some projector. Here, in this case, is this. And then this would be complicated function of the parameters. But in the high temperature limit, you expect some simplification. You have in that case, you expect you have many charges in the manifold that are produced by the temperature, and these charges are random, and then let's say the representation of the vacuum in terms of charges is just the tensor product of infinitely many representations with equal probability, and this thing always converges to the regular representation of the group. And the regular representation is just the one in which the expectation value, let's say in this case of the elements of the group, is 0, except for the case of the identity. So in that case, you expect that these partition functions just go to applying that to this projector, you get 1 over G. So if you put it in your Renyi entropy thing, you get U0 at 0, because when x equal to 0, the two intervals are very separated, and this is always true. And when you go to the limit of they touch each other, it's like the high temperature limit. And in that case, you get for this just minus log G. Minus log G is the signature, and it's different from U0, so there is no symmetry. So this number at the extreme of the case, when the intervals touch each other, or the high temperature limit in the case of the partition function, is just a signature of the size of the violation of Haag duality, or the size of the violation of non-completeness. And in the more general cases, you can think the same. You can think that you have some dimensions of your sectors, some dimensions that in general in 2 dimensions will not be integers. And then this number log G is replaced by log of some number that is called an index. And algebraically, this index is the index of inclusion of the complete theory in the theory you are looking at. So there is a size of the complete theory with respect to your theory, and this can be thought as a sum of dimensions. And then in the limit of high temperature, you would get that this U2 at the point 1 is just the logarithm of this index, algebraic index, that just replaces log G in the case of a group.
And sorry, and if we think of this log G as the entropy of these charge operators that were not captured by the local operators.
Yeah, well, it's something like that, but is that entropy is some kind of it's a kind of limit in the high temperature thing, right? Because there are infinitely many charge operators, but you only care, in this case, you only care about the representations. So two different charge operators of the same charge are considered somehow the same object because they differ by the additive algebra, let's say. So you only care about the different charges, the different representations, right?
Right.
Okay, but this is just a limit of ratio of partition functions, and you get this number. It's interesting that in this limit, high temperature limit, this number is purely, let's say, kinematical. It doesn't have any dynamics of the theory inside. It will be the same for any two models that have the same index, the same group, let's say, between them. And you can also, this is somehow not completely satisfactory from our point of view, because you have to appeal to a complete theory. You are interested in the theory tau that doesn't have that is not complete, and you are appealing here to the complete theory to get a number, but in fact this number depends only on the theory T, and there is a theorem by Longo that defines another kind of index, now an index between two algebras that are one inside the other. But in this case, it's two algebras that are one inside the other, but these are the algebras, the maximal algebra and the additive algebra of the same theory tau. The same theory tau for two intervals have an additive algebra and have a complete algebra, let's say, that is the commutant of the outside part. These differ, and these have also an index. And this index is called mu, is the global index. And these are simply related, the global index with respect to another theory are related to this lambda square here. So it's very beautiful formula. So in that case, you can just write your U1 at the extreme as a 1/2 logarithm of this mu that only depends on your theory and not in a completion, let's say. It only depends on the theory. All this you can see more practically in this way. Suppose you have a complete theory and you make the low temperature limit of the partition function, it gets something, and then you get something exponentially small, because this comes from the vacuum, let's say, from the Casimir energy, and the other things are exponentially suppressed because you are at low temperature and you have a gap in the spectrum. If you have a modular invariance, the same will happen at high temperature. You have a high temperature term plus exponentially small things, because it will be equal to this object here, right? But then if you break modular invariance, then what happens at high temperature is that this is violated. You have this term, but then you have some subleading constant term here, that is this index, that will add to, and then you have exponentially suppressed terms.
So, Horacio, just one question. So this equation mu tau is equal to lambda square mu c. Roughly, how does one see that it's lambda square?
Sorry, I couldn't get the final part exactly, but this formula is telling you how to relate. These mu's are depending only on one theory, and they compare the size of the maximal algebra and the additive algebra of two intervals in your theory, these mu's.
Yeah,
And
no,
this
I
lambda-
understood. I understood that. So I think this tau is standing for this R region and the mu C is the algebra of the commutant of the complementary region, right? Or the opposite?
No, this tau is the name of a theory, and this mu tau is just the size of the inclusion of the algebras, exactly, of the commutant of the two intervals with respect to the two intervals. But the same here for another theory, the same here for another theory. And this lambda is just relates the two theories between each other, the size of the two theories. So,
sorry, but now I thought you were talking about a single theory.
for a single theory, this mu is just, forget about this size, the thing. For a single theory, this is comparing the size of the algebra of the two intervals with the algebra that you get taking the commutant of the outside part of the two intervals.
Okay, so how do I see that that connection is that mu t is equal to lambda square times mu c? How does one see that? Is there a way to understand that?
Okay. Well, no, it's not immediate, but you can feel that it's going to be the case because you have two intervals. So you have two intervals. So this lambda is just the size of one theory with respect to the other in a single interval. So as you have two intervals, this lambda will be square because you have two intervals in these mu's. Right? This is a little bit of explanation.
Okay. Okay.
Okay.
Yeah, thanks.
Well,
Can I, sorry, Horacio, just to understand this slide little, try to understand a little more physically, is the point that once you are in the high temperature limit, you are going to produce all charged excitations. Just because that's the nature of the very high temperature limit. In the complete theory, you have modular invariance, and you can always look at it appropriately as the low temperature limit after doing the duality. But in the incomplete, so to say, theory, you have restricted at low temperatures to only neutral operators, and that's a very big change compared to what you do.
Exactly. Yeah, and it's a change that is somehow non-local on your. You have your soup of charges, and it's a change that is non-local because you are not doing nothing particular to some charges there, but to something global, right? You are saying, well, of all these excitations, I take only neutral ones, but globally neutral, right?
Sorry, but I thought the restriction was at high temperatures. The high temperature answer is modified by this thing, by this extra factor, I thought. The low temperature was unchanged, and the high temperature guy had this extra. Because at high temperature, every sector is equally excited, and so you get a factor of 1 over number of sectors.
Exactly. Yes, it's a very simple thing. In fact, yeah. At the end, it's very simple. Then, if you want to say it precisely or show it precisely for all models, then it's a little bit more work, but it's just that, yeah. But then, for example, how do you compute the things for in a CFT if you build up your CFT with chiral models, right? You have your chiral CFT. Let's think you have let's say minimal models, and then you have your chiral characters, and then these chiral characters have modular transformation matrices. They transform under in the usual way under modular transformation. And then you define your model just by a coupling matrix, just coupling the right and left fields. So your fields, or the fields of your theory are going to be products of fields in left and right chiral algebras, let's say. And then modular invariance is in general thought as this property of the coupling matrix that commutes with S matrix that appears here in the transformation, and the T matrix that appear here in the transformation of the chiral characters, right? So one commentary is that this T symmetry is implied by locality of your CFT. If you think your CFT is a local quantum field theory, then this T symmetry has to be there, because this is related to the fact that the H's that appear in your fields are in the left and right component have to differ by an integer, and this is necessary for causality, because the correlation functions are given by this way and have to be in the Euclidean plane, have to be real analytic functions, single valued, and then if your fields are causal, then you have to have this T symmetry. So the question is this S symmetry, and this S symmetry is not mandatory, and you can compute. You just, well, these are the forms in which these dimensions now for the chiral sectors. The chiral sectors have these dimensions that come from the chiral characters, and then this is the mu of the chiral theory. Chiral theory is also a local one. For example, the chiral stress tensor, and you can compute the mu, and the mu is 0 to the minus 2, is the sum of dimension squares. The mu of this global index of two intervals is given by this formula for the chiral theory, but you want to compute the mu for your theory that it now is two-dimensional, has the two chiralities, and is given by this coupling matrix. And then you can just apply our previous formula and look at the L0 limit for this ratio of partition functions, and using the property of these chiral things, you get this number. So you can actually compute from the dimensions of the chiral characters and the coupling matrix how is your index in the two intervals, and this is the number that will appear in the limit of the partition function. Well, this is just a commentary that it will be complicated to explain, but you can prove that this is going to be 1 if your theory is complete. So it doesn't look like immediate, but it's going to be 1 for complete theory. In particular, if you have a diagonal model in which this M is just delta ij for all, is immediately true that this is 1, right? But then, of course, this M you have to select in such a way that the theory closes into itself, has closed an algebra. This is more difficult, and you can see that there are many models that are non-modular invariant and that are well defined as field theories in 2 dimensions. For example, this is the Ising model, C equal 1/2, and then you have the usual Ising model is this one that you have here. This is a bosonic one, or you have the fermionic one that doesn't have the sigma field, that is just a free fermion. And then this is a stress tensor, and then you have intermediate subalgebras that close into itself. This is just a chiral fermion, the other chiral fermion, and here you have an algebra that is inside the two completions. So it's important, and here you have the same for the tricritical, the next central charge. You have many models that are closed algebras, and you have these non-diagonal, diagonal complete models. So in general, it's interesting that in 2 dimensions, for example, for the stress tensor, for any other model, in general, you have more than one completion. You can go to a completion, you can go to other completion, and here you have this completion and this completion. Just adding operators, you get to different completions. But in dimension greater than 2, the same problem has only one unique completion. If suppose you have and it's always related to a group symmetry. In more than 2 dimensions, this problem of Haag duality violation on 2 balls is always related to a group symmetry and has a unique completion that is the one that one had in mind. It says I add the charges and that's all. The difference, of course, with 2 dimensions and high dimensions is that in 2 dimensions you can add the charges, but you can also add the twist. So and these are incompatible to each other. So somehow there are more ways to complete the theory. So the twist, that is something acting on an interval, can be thought as 2 operators acting on the end points of the intervals, and in such a way you can complete the theory in different ways. You can compute in the Virasoro case, this is the index for any m for the minimal models, and you can see that it diverges as you go to m equal to 1. All these submodels are classified in this paper for all m, and it's interesting that it looks like when you get to m, to more central charges, m greater it will have many submodels, but it's not true. It saturates to something like 8 submodels or something like that, and it's interesting to look at that. Well, this is just as my time is going out, I just go briefly through this. This is you can think in other Renyi entropies, not just n equal to 2. In the n equal to 2, the idea was that you had 2 copies, and with this you transform to a torus. And in order to see these non-complete models, you can think you are projecting, you have projectors acting on one of the intervals, for example, killing the charges somehow, and these are going to be parallel projectors that are the same thing, because 2 parallel projectors, p squared is equal to p. So you in fact get the torus with a projector, and then it's the thing that we have been talking about. For 3 things, for 3 intervals, you get mapping not to a torus, to something with it's a kind of torus with 3 handles. And then you have these 3 projectors, but one of them is irrelevant because with 2 already, the charges here are neutral. So you always get n minus 1 important projectors, and at the end, if you compute the limit of x equal to 1, so when the interval touch each other of the Renyi entropy, is always giving you the same number. So it's giving you the same number. People call this flat spectrum. It doesn't depend on the Renyi index. Well, you can also think in cases where the index is infinity. For example, if your group is not finite but is a Lie group, then your group operations is not going to have 0 expectation value, but it will get to some Gaussian distribution near the identity, and with that you can compute the ratio of partition functions in the limit of high temperature is not going to get a constant, but it's going to grow logarithmically. And the same for the Renyi entropy. In the limit is not going to go to a number, that the index is going to be divergent, and in particular in 2 dimensions it diverges like a log of the cross ratio.
So an example of this would be just a U1 charge.
Exactly. For example, this is in the U1 charge. For example, the free fermion is a complete theory, and you can take the U1 orbifold, or you want a neutral part of that, and it's just the current what you get, and the current is equal to the chiral scalar. So the chiral scalar is the U1 fixed point of the fermion, and you expect the chiral scalar then to have an infinite index like this, something like this, where this G is the number of generators of your Lie group. In that case, it will be 1. And in the chiral scalar, you can compute exactly the UNs, because it's a free theory. It's complicated calculation, but it has been done. and then you can take the limit of x equal to 1, and you get exactly what you expect with 1/2 here. Another example is the Virasoro net for c equal to 1. Then you can apply this in A2 case, in the A2. Here it was for all n, and here it's just for A2, the asymmetry for index n equal to 2. You can compute it just from the partition function that is known because of the character of the identity of the c equal 1 model, you know, and it gets this, and you get the high temperature limit, and you get this thing. And you get a 3.
Virasoro net means restricting to identity sector.
Exactly, it's just a stress tensor. It's a stress tensor and the algebra generated by stress tensor. Yeah. And in this case, you get a 3/2, what means that you have, it looks like the Virasoro net is the orbifold, is the neutral part of something under a group that has 3 generators, right? Well, and it's true, it was proved by Renyi in 93 that the Virasoro net for c equal to 1 is the fixed point of the chiral algebra SU2 level 1 under the global SU2. It coincides with this thing. So in fact, from here you can see that it will have a 3 log term in the limit. And then what happens for c greater than 1? And for c greater than 1, what happens is that naively, if you do the calculation just using the character of the identity for c equal greater than 1, you get that U2 diverges in this way. So it's not a log, but something much bigger is a log. So it's natural to think that it's correct because it's in that case there are many sectors. It's like too much for a Lie group symmetry, let's say, from a complete model. But still, you get some dependencies of C that we think is highly suspicious. So we think that for C greater than 1, we do not know for the Virasoro net. We do not know exactly how to compute the U2, for example, because one wouldn't expect a dependency on the central charge, right? For in the limit of large central charge, you have only the stress tensor. You would think you have only one field. You would not expect something growing with the central charge. And we think that the usual formula relating the Renyi entropy with the partition function, the torus, is not applicable here, because this theory is quite strange. It doesn't have something that is called strong additivity. That is the fact that if you have the algebra of 2 adjoint intervals, this will generate the algebra of the 2 intervals. So somehow the OPE of projectors on the neutral algebra will go to the projection, and we use this here. For example, you were using 1 projector instead of 2 here. So there are several things that would go wrong. So I think it would be interesting to understand what happens for the Virasoro net for c greater than 1, because it doesn't seem that the usual formula using the partition function of the torus for n equal to 2 is correct. It doesn't seem correct. Okay, and this is my last thing, is what would you expect in higher dimensions? In higher dimensions, you would expect some kind of modular thing, modular symmetries for this type of manifolds, products of SU1. But of course, these are very difficult to express in terms of the modular data, the dimensions of the theory. You would expect rather, you would be interested rather in this SD-1 times S1, the usual thermal partition function, and that where the energies are given by the spectrum of the theory. But this doesn't have modular symmetry. However, some people here, some papers, have said that still you expect something interesting in the limit of high temperature, because in the limit of high temperature, you can think the partition function in terms of a thermal effective action. So in that case, the action, the partition function is basically produced locally. So you expect, for example, in d equal to 4, something growing like volume times temperature cube, plus some subleading corrections. And subleading corrections will be given also locally by curvature terms in the sphere. And these curvature terms will only jump by two powers. So if with this idea in mind, you see that here you don't have, for example, in d equal to 4, you don't have constant term. But then if you have the subalgebra by a symmetry group, you immediately get this constant term. So you can immediately point out where the model that you have, all these things you can in principle compute with the spectrum theory. You can point out where the theory you have has can be extended or not by the existence of this number. That has to be a logarithm of a natural number, right? Otherwise, something is wrong. Well, and this thing can also be by a Laplace transformation, can be expressed in terms of the density of primaries. For example, in 2 dimensions, the existence of this index changes the constant term in terms of the expansion of high delta, high dimension. And in this case, it will only allow you to determine if the theory has Haag duality violations only for even dimensions where this constant term doesn't appear in the usual expansion. But if you have a Lie group symmetry that is a logarithmic term, you get a logarithmic term now instead of a constant one, and then you can, in principle, distinguish whether you can extend the model by a Lie group symmetry in all dimensions, even and odd, because these log terms are given by universal terms in the usual expansion for complete theories. For example, in 4 dimensions, you expect a 4/3 term instead of this correction. So this ends my talk. So I have said that Haag duality violations of generalized symmetries is a lack of completeness, let's say. The expression of this in terms of the CFT data of this lack of completeness in d equal to 2 is understood, is a violation of modular invariance, and modular invariance is completeness for d equal to 2 CFTs. In higher dimensions, Haag duality violations for disconnected regions are associated to symmetry group and detectable in principle through the asymptotic of density states, at least for even dimensions. The difficult question is how to detect higher form symmetries from the CFT data, and we have no clue. And that's all. Thank you.
Questions, Zoom audience first, maybe?
I have a question actually. Hi, Horacio. So there was
Hi.
a formula actually for minimal models, where the incompleteness was written as some, function of M, where M parameterizes the minimal model, right? Can you just show that slide?
Yeah. This
No, the one.
formula, can you see that?
Yeah, I can see it, but I'm talking of the minimal models, this formula, which is next to the central charge, 1 minus 6 upon m to m plus 1. Just slide before this. No, you had a formula for minimal models for C less than 1, right?
Perhaps this one. This one.
Yes,
So
exactly.
this is the global index for the stress tensor for the identity in the
Yes,
minimal model for the identity.
right. So now if you look at the large M limit of this mu of M, then, because you'll get sine pi essentially in some sense. So
Yeah, this diverges. Diverges like I think it's like m to the fourth or something like that.
yes. So
yeah.
what does it mean? Because M becoming very large is basically going towards C equal to 1, right?
Exactly. No, it means that the index of this thing, so it means that you have more and more and more charge sectors in order to complete the theory. That's the main point. In order to complete the theory, you have more and more charges. You have to add more and more charges, right? That
I
are
see.
the primaries.
I see.
In
Okay.
the case where your central charge goes to 1, in that case, diverges really. This was here, right?
Yeah.
For central charge 1, the stress tensor this is a Virasoro net for central charge 1. In that case, the limit as x equal to 1 is divergent. It's log term
Right.
time you have. So really, for c equal to 1, you have infinitely many, let's say, charges. Yeah. So it's divergent, really. And from there to c greater than 1, the Virasoro net has always divergent index.
I see. Okay, thank you. Thank you.
Horacio, can I try to put your result in the following way just to see? Because suppose I feel uncomfortable about about theories which violate modular invariance, just suppose. But even in such a case, I might be interested in the following type of question. Say I'll say it in terms of entanglement, but then we can put it in terms of mutual information. Say there are two regions and we want to define the entanglement between them, then as you know very well, of course, the deep way to think about it in terms of the algebra or the operators in each region. Now, maybe instead of using all the operators, we only want to use some subset, say those which are neutral under some symmetry, and then ask about how much entanglement there is, say between two regions or a region and its complement, whatever. In that case, perhaps, I mean, the theory is complete, but we are asking a question about what parts of mutual information or entanglement are coming from subalgebras. And then your index mu might still give us information about that. Is there a way to think about it like that?
I think somehow, yes. Suppose that you have your theory in the circle here, and then you are thinking only on the neutral operators here and the neutral operators here. So you have two intervals.
Yeah.
And then you have the neutral operators in I2 and neutral operators in I4 is another two interval region. And then exactly what happens is that the entropy for your algebra I1, I3 is not equal to the entropy of I2, I4 in the neutral operators. Exactly.
Right.
Yeah. If you have the neutral operators I1, I3, then the commutant will contain the neutral outside plus something that is charge anti-charge. And this will have exactly the same entropy, but it's a bigger algebra. Right.
It's a bigger. Yeah, exactly. Okay. So this, in a sense, measures that mismatch, right? Between using.
Yeah, exactly. The index measures that mismatch. Of course, when these intervals are whatever intervals is difficult, it's a complicated number that depends on the cross ratio. But when they touch each other somehow, then the mismatch between the entropies is just the index, this number that is purely is purely geometrical or kinematical, let's say, just measure the symmetry that you have.
I see, got it. Okay, thank you very much. Thank you.
Okay.
Any other questions? So in the situation where things were behaving funny, where you didn't have your Haag duality, in 2 dimensions there was a lack of modular invariance, and in this higher dimensions this local effective action didn't work. So in both cases, it seems like if you take the theory and you try to put it on a general manifold, a manifold with a general metric and maybe a general gauge field coupling to U and to global symmetries, and if you demand that the effective action when you do that has all the properties you want, is diffeomorphically invariant and so on, then you had your Haag duality. So is that right? And is that supposed to be like a two-way statement?
I don't know if I understood completely what you said, but somehow it's important in this argument that modular invariance for the case of the index, right? So of course, modular invariance in 2 dimensions is related. Exact modular invariance is related to exact. So you have this property that is very strong. You have a violation of Haag duality, give you violation of modular invariance and one-to-one thing. But still in higher dimension, you cannot aspire to something so beautiful as this thing, because in higher dimensions, the torus, let's say, is not there. It's just an s d-1 times circle, right? So you cannot aspire to something like this. But still, with this argument that people made of the large temperature partition function that is local in the case you have a, let's say, complete theory, because in the non-complete theory you can think you have the same thing but some projection that is non-local. So the argument that leads to think of this thing is broken, and then you get some different number there that produces some mismatch with this partition and get you something there. So in some sense, you don't need the full modular invariance. You just need the limit to say something. The limit when you have high temperature. I don't know if.
Right. I was asking about the principle. Now, the principle involved in the analysis of these papers that you are talking about here is just that if you take the theory on an arbitrary manifold, which has a circle and the circle is small, you get an action that is that respects all the symmetries. So, for instance, the dependence on the metric is just through the curvatures and so on.
Yeah.
Using no other principle, you get the form of the effective action, which didn't have this constant term. So it seems like that what you're violating is that principle that the partition function on an arbitrary metric is diffeomorphically invariant if you don't have your argument, if you don't have your whatever completeness. And this seems similar for the case of 2 dimensions, because in the end, modular invariance in Euclidean space is just that the partition function is diffeomorphically invariant. You don't care what you call space and time. So it seems like that's a unifying principle.
Well, it could be a connection, because there should be kind of connection with this idea that you can with diffeomorphism invariant, in the sense that people say, well, for a theory of gravity, you don't have to have any generalized symmetries. You have to kill all those things, and these generalized symmetries somehow are ruining somehow your idea that the path integral is just a geometric object.
Interesting.
Because you have to add something else, something on top of that, to define the partition function. then perhaps there is a connection also with what you're saying here in the high temperature limit, that in order to produce this part, of course, the idea of these papers will not hold if you have this type of sectors, let's say, or
Yes.
symmetry, right?
Will
So
not go
that's
ahead. Only assumption made in these papers was diffeomorphism. There was no other assumption.
okay. Yeah, okay.
See, just to make sure I understand the connection with generalized symmetries, so you of course gave this example of the charge and the neutral sector, but it's true in general that if one has generalized symmetries, you violate Haag duality, is it? Or this notion of completeness, is that right?
Yeah. This is our people that works in generalized symmetries use a very different language, but as far as we can tell, when the generalized symmetry exists, is because you have a Haag duality violation, and is the same phenomenon is explained in a different way, let's say. But for us, let me say more precisely, with regard to the local physics, these generalized symmetries are just Haag duality violations. Then people think what happens with these generalized symmetries when you put in a non-topologically non-trivial manifold, etc., and then you can have, I don't know, depends on what you define the theory in a topological non-trivial manifold, etc. But as far as the physics of flat space is concerned, generalized symmetries can be defined through these Haag duality violations, for us are the same thing.
Okay. Thank you very much.